Are you a ham interested in digital modes? Want to know the components you need in order to set up your digital station? I have answers. Welcome to Ask Dave, episode 25. I'm Dave Kassler, amateur radio call sign KE0OG, here to talk about digital modes. Many hams find that using computer-to-computer conversational modes to be a nice next step after getting your HF station set up. In this video, we look at how these signals are created and how you can set up your station to take advantage of them. Let's start with CW and work our way up to the latest digital modes such as FSK This video gets you set up. The next video will talk about actually operating these modes with sample QSOs. Let's start with CW. A CW transmitter puts out a single tone on a single frequency and then turns it on and off in accordance with the Morse code. We see this on our frequency display as a single tone, shown here as 14.051 megahertz. The CW receiver is actually listening to either lower sideband or upper sideband. In this case, we'll use upper sideband. The receiver injects a tone 1 kilohertz below the received signal. The receiver then takes the difference frequency, 1000 hertz, and sends it to the headphones or speaker. The listener hears nothing if the transmitting station sends nothing, but hears the 1000 hertz tone if the transmitting station is key down. This is how all CW receivers work. The thing I want to point out here is what's actually in the receiver passband, a single tone. Now, for a brief review of single sideband, in this case upper sideband. The audio speech signal is created as shown here, taking up a bandwidth of about 3 kilohertz. Then, before transmission, the carrier is suppressed and the waveform is transmitted. This is ordinary SSB. Okay, now for the magic. Let's take that same SSB transmitter, but instead of the audio input being a speech waveform, let's suppose it's a single tone. So we have the carrier frequency plus the single tone at, say, 1 kilohertz. The transmitter suppressed the carrier. Look what's left to go out over the air. A single frequency. Does this look familiar? Yes, it is. But I point out that for this to work, that is, generating a single transmitted tone using an audio input, the carrier must be suppressed as much as possible, as is normal SSB practice. The transmitter's audio and signal circuits must be as linear as possible, otherwise harmonics will show up, and the transmitter can't add broadband audio noise. It has to be quiet. So let's do a direct comparison of what's transmitted by a traditional CW transmitter and what's transmitted by an upper sideband transmitter being fed a single audio tone of 1000 hertz. The answer? If done right, you can't tell the difference. We've just discovered a way to send CW by using an SSB transceiver, and yes, this works. Here's what it looks like. Note that we are using a tone generator as the input to the transceiver operating in single sideband mode. So, as we vary the tone, the frequency of the transmitted tone will vary too. Now, let's add another layer of complexity. Radio teletype is transmitted using two tones. The transceiver diddles back and forth between the two tones using the Baudot-Murray code. Well, can we create that using something that generates two audio tones and then send this to a single sideband transceiver? You bet. So, in the traditional setup, there's a teletype machine on what's called a local loop that is managed by the terminal unit, or TU. The output of the TU tells the FSK transmitter which of the two tones to send. Many medium and higher-end transceivers today will accept these inputs and create truly frequency-shifted keying, or FSK. But look at the next row. The machine, or a computer emulating the machine, talks to an audio tone generator. The tone generator generates the two audio tones as instructed by the TTY machine. The two audio tones are fed to this single sideband transceiver and are put out on the air. Since this process is done using audio rather than directly, it's called audio frequency shift keying, or AFSK. Done right, this looks just like FSK on the air. By the way, the purists absolutely insist that AFSK just isn't an acceptable substitute for pure FSK. Done right, the two look identical on the air, and FSK and AFSK are completely interoperable. But note the caveat, done right, clean linear transmissions. Now, ready was the first real digital mode and has been in ham radio for many decades. I made my first radio teletype contact back in the late 1970s using a real Model 15 teletype machine and a hacked VFO that would change frequency in response to the output of the machine. It was true FSK. Back then, that was the only way to do it. But then something important happened. The Tucson Amateur Packet Radio, or TAPR organization, started developing ways to emulate Internet-type communications on 2-meter FM, at first emulating old AT&T modems and using an amateur radio-purposed packet protocol called AX.25. The result was packet radio and is still found here and there today. Two tones would be used to transmit information. The device that did this work, creating the tones for transmission and deciphering the tones on reception, was called a Terminal Node Controller, or TNC. The floodgates opened. Pictured here is a truly seminal device introduced by Advanced Electronics Applications in 1986, the PK232. This built on the TNC idea, but broadened the number of modes substantially. The photograph shows mine, a very early unit. Basically, the PK232 is a computer in and of itself. In fact, you don't need a computer with it, just an ASCII terminal. The PK232 would generate the audio tones needed for any digital format then in use and send these as audio input to a transceiver. It would then decode the audio output of the transceiver. The PK232 did packet radio, but also had several other modes. It was an early implementation of APRS, the Automatic Position Reporting System, still in use today. It also did RTTY using AFSK, but it also included some additional modes designed just for HF. AmTOR was an amateur version of SciTOR, an error-free communications method used by ships at sea and other point-to-point services. PACTOR was designed especially for amateur radio and had much higher throughput than AmTOR and eventually replaced it. The PK232 could even generate Morse code using audio tones, although it wasn't very good at deciphering it. As the PK232 product developed, it went on to include a mail drop feature as well as a bulletin board system. Truly, the PK232 was a game-changing device. Now, I mentioned that the PK232 was used with an ASCII terminal. If you've seen one, you're probably about as old as I am. They were common about the time that personal computers became popular, and a PC could be used to replace the ASCII terminal by using terminal emulation software. Pretty soon, PCs became quite good, and ASCII terminals faded away completely. Back when the IBM PC was new, the computer itself was pretty basic. Companies sprang up to create cards that could be inserted into the computer to do various things. Many devices were developed, but the one of interest here is the sound card, literally a card plugged into the computer that could both create sound and interpret it. The idea that computers could both make and play music as well as record it was revolutionary. It didn't take long for hams to figure out that if a sound card could create music, it could certainly create the audio tones needed for packet and AFSK. In other words, you could skip the PK232 and its competitors and just connect the sound card's audio input and output to the transceiver. A separate path was needed to key the transceiver, that is, tell it when to transmit and receive. This was usually done via the RS-232 port that all personal computers had back in those days. So we see the transceiver interfacing with the computer for transmitted audio, received audio, and the push-to-talk control line. It wasn't long before people started to take advantage of the sound card. In 1998, English amateur radio operator Peter Martinez, G3PLX, made use of the fact that the sound card, even back then, was a powerful signal processor. He created a mode called FSK-31. It was designed specifically for the sound card, and the hardware TNCs were shoved aside. With the introduction of Digipan, simple software that could create and interpret the FSK-31 audio tones was now available, and digital modes exploded like wildfire. By then, sound cards were so ubiquitous that they were incorporated into the computer motherboard, a practice followed to this day. People would connect the radio's microphone and speaker directly to the sound card audio input and output. By the way, that's how I did it when I first tried it. I jumped on this quite early. I had to create a homebrew device to take the RS-232 output and use it to key the transceiver. But issues quickly arose in the amateur radio community. Connecting the audio is fine, but when transmitting, it's a great way to create RFI in those audio cables, and ground loops became an issue. Also, transceiver audio input and output levels were an issue, and getting everything set right was tricky. Also, since people were using the computer's main sound card, the normal noises, beeps, and tones that computers create would end up getting transmitted over the air. Transmit-receive switching, or push-to-talk, was always an issue, particularly since, as personal computers progressed, they started moving to USB and away from RS-232, which has now entirely disappeared. Well, ham radio equipment manufacturers stepped up to the plate. West Mountain Radio was first out of the gate with its Rig Blaster products, one of which is shown here. It had audio isolation so there wouldn't be ground loops. It also had ways to adjust audio levels going in both directions. These devices became very popular and made getting on the air with digital modes much easier. Digital modes began to proliferate. The next step was a giant conceptual leap. Windows by this time could handle more than one sound card, so a company called Tigertronics created a USB-connected external sound card designed with digital modes in mind and called it the SignalLink USB. It had complete audio isolation and level control built in. Further, by means of jumpers and cables available as part of the purchase price, it could connect any radio to any computer. The photo shown is of mine, which provided excellent service with my Tentec Jupiter for more than a decade. Other companies jumped in with competition, of course, but the SignalLink is still quite popular. The box could set signal levels easily, plus it had a built-in circuit to sense when the computer wanted to transmit and thus provided push-to-talk to the transceiver. These little things made digital modes easy. Because it was a separate sound card from the main one in the computer, the extraneous Windows sounds no longer went out over the air. Radio manufacturers caught on to the digital mode popularity quickly. Here are 3 generations of radios, all from my collection. The top one, the seminal FT101, which was one of the first full-featured transceivers, offered only the microphone input and the headphone or speaker output for sound. The middle generation, exemplified by the Ten-Tec Jupiter, had special connections for digital audio. They provided something called line-in and line-out, which are audio connections at a constant amplitude, so levels had to be set only once. This configuration remains very common today. The bottom shows my Yaesu FTDX 3000, and it has leapfrogged past the external sound cards to having a built-in sound card itself. So the only connection between the computer and the radio is a simple USB cable. This will be the trend of the future, but so far appears only in a few radios. Okay, so we have several parts here. The computer generates tones via a sound card. The tones go into a transceiver for transmit and come back out on receive. Many modes have been developed specifically for the sound card and have almost entirely supplanted the old modes used by the external TNCs and multimode data controllers such as the PK232. The astounding signal processing power in a common sound card is amazing and has led to modes beyond PSK31 and its variants to include modes such as MFSK, MT63, Olivia, Contestia, Thor, and Throb, as well as the recent and very popular JT65. Oh, and since there's nothing to limit a sound card to just purely digital, you can use it for slow scan TV as well as Hellschreiber. Truly amazing. But, and this is important, once you are set up for any sound card mode, you're set up for all of them. The truly popular ones these days are PSK31 and JT65. Well, okay, something has to instruct the sound card as to what to do. There are many, believe me, many different software programs out there. Good old Digipan is still available, although it was last updated in the year 2000. It assumes using an RS-232 to control push-to-talk, so its relevance has diminished to near zero. For general purpose use, FL-Digi is very popular, very capable, and is free. Lots of people use it. The WSJT software is not general purpose and is used for JT65, JT9, and other modes not usually found in the general purpose programs, and is also free. If you're willing to pay extra money in order to get a little bit more support, MixW and Ham Radio Deluxe are available. I use an earlier free version of Ham Radio Deluxe, but to help prepare these videos, I downloaded and installed FL-Digi and have had several successful PSK31 QSOs. Now, a warning. Given FL-Digi is free, its programmers can't afford the internet server service needed to support many downloads of large files. So they use a service called SourceForge. You get the software from SourceForge. But since SourceForge itself is free, the site is plastered with sometimes misleading advertisements. Be very careful you're downloading the right thing. I will post a separate video that shows the downloading process. I will also post a separate video showing a complete PSK31 QSO with my commentary so you can see how it works. Once you have your station set up for sound card digital modes, it's actually pretty smooth sailing from there. But setting it up can be hard. I say this because I've torn out lots of hair getting it working. There are many ducks and they all have to be in a row. Your station situation is unique and you'll need to work through your issues. You need to set up your computer and put in the right parameters. You need to get the interface device set up for your transceiver. And you need to set up your transceiver's audio chain to be completely linear, and so on. I suggest you contact fellow hams at your local ham club who can give you one-on-one mentoring on going from having the parts to having a working system. But when you do so, an entirely new world awaits. I took this photo on April 19th, 2016. Yep, that's snow. When will it ever be spring? April weather can be fickle, to say the least. This photo was taken from our dining room and looks out at Mount Sneffels, whose peak at 14,150 feet is about 15 miles from us. So, dig into the subject. There are gobs of websites devoted to this stuff, as well as many articles in QST and other publications. I point out the ARRL book called Get on the Air with HF Digital, good for beginners. I hope this brief summary has helped. If you liked this video, please share it with your friends. I urge you to subscribe to my channel so that you can get notification of future videos. I have a tip jar on my YouTube channel page and also on my website at ke0og.net. The whole purpose of this series is to answer your questions about ham radio, especially those of interest to those new to the hobby. You can ask questions by commenting on any of my videos on YouTube, preferably on the one most directly related to your question, or you can pose a question directly at www.ke0og.net/ask-Dave. Until we next meet, 73.